All right. So I'm going to start off like we usually do. How's the homework going?
Can we look
Questions
at,
on any of that?
yeah, can we look at number 30?
Yeah, I was gonna
Uh,
ask the
29.
same exact thing.
Hold on.
Okay, so hold on. So number 30 and number 29, which section is that?
2.2.
2.2.
Okay. Any other ones?
There's there's a lot to 30.
Okay.
What's that? There's a lot to 30. Can we just look at the one that where RS is greater less than Q?
I would like 30 and 24.
All right. Well, then let me go ahead and share my screen. And I'll see if I can get us to that page, see if I can beat the screen. Nope. Okay, so I heard 30, 29, and 24. I'll be happy to kind of like walk us through all of these. And then maybe not do all of it. So 24, we'll start with that. Let me just go ahead and write this down and then I'll go back to the whiteboard. All right, so let's go to the whiteboard. So we've got y prime equals 1 plus y squared over 1 plus x squared. And it says we want to find the solution to this explicitly. So we want to write it as y equals. So first thing, recognize that this is separable. So we can write this as dy over 1 plus y squared equals dx over 1 plus x squared. And then integrating both sides of that, we're going to get inverse tangent of y is equal to inverse tangent of x plus c. So nice and quick. And now when we go to solve for y, we're going to do the tangent, get the tangent of this. So y is the tangent of tangent inverse of x plus c. Hold on, not plus c is in the tangent. So this actually is our explicit form, or a form of the explicit solution. So we could stop here, but we can be a little bit more eloquent if we use that sum of angles identity for tangent. And so what that would do is make this tangent of tangent inverse of x plus tangent of c divided by 1 minus tangent of tan inverse of x, times tangent of c. So that's the identity. It's tangent of alpha plus beta is tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. And so on that little hint, you know, where it said use this, that's the this they're wanting you to use. But the reason we do this is because the tangent of tangent inverse just reduces. So we end up with y equals x plus the tangent of c divided by 1 minus x times the tangent of c. So it ends up being kind of a nice little form. It's not too terrible. And in fact, once that c is determined, this ends up just being a rational function. All right, so how we feel about that one? One of the many places where our trig and algebra experiences come back and make this a little bit simpler in the end.
Yeah, it was good. It was just that simplification.
Yeah. All right.
Bruce,
So I'm going to go
real
back
quick.
and share the screen again so we can go look at what the next one is.
Hey, Bruce.
Yeah.
Hey, you said that the y equals tangent, parentheses, tangent inverse of x plus c was like an acceptable answer. So you would take that on a test, I'm guessing.
Yeah. Like if this was an exam and I just said solve this explicitly, if you wrote it as tangent of tangent inverse of x plus c, that's full credit.
Cool.
The issue with this one is that it's not as easy to use. And so if we're actually applying this to something, like if we're doing some sort of population modeling or whatever that led to this differential equation, this thing is cumbersome and it doesn't actually show you the patterns. You know what I mean? Like when we actually see this next one, or when it's that other form, it tells you a little bit more. And so when you have composition of trig functions, trig and trig inverse, you want to get rid of them. You want to simplify if possible in general.
Okay.
But you're right. Yeah, if this had been a homework, or sorry, an exam question, I would have been fine with tangent of tangent inverse of x plus c.
Cool.
All right, so let's go ahead and go back to this sharing screen again. It looks like Brennan's having trouble getting into the class, so. But here we go. So here, we're going to look at 29. So 29, epidemic spreads through the population at a rate proportional to the product of number of people already infected and the number of people susceptible but not yet infected. Therefore, if S denotes the total population of susceptible people and I denotes infected people, then we get this. All right, so we actually kind of, oh, sorry about that. We kind of did this problem. So last time it was one of the examples, maybe not last time or 2 times ago, it was one of the examples I showed you where we could use separation for something that was a little more complicated. So this was the one that gave us logistic growth. I wrote it as y prime equals ky times L minus y. So if you go back and you look at your notes, we've actually already solved that.
Yeah.
But the one thing I do want to do, since we now have an initial condition, let's plug in for that and then see what happens as t goes to infinity. So if you go back and you look at your notes, and I happen to have my copy here, so I don't have to redo the whole bloody thing. Find it here. So what we ended up getting, I'm going to go ahead and stop share and go back to the whiteboard here. So we got y equals, it was L over 1 plus C e to the minus LKT. So that's what we found when we did it the other way. Let's just replace all the letters. So Y is now I, L is S, because that's our susceptible population. The C is still C, that was just the unknown that we get from integrating. And then the minus LKT, that should be minus SRT, because we had that growth rate of R. So I just translated this. But now let's use the initial condition. They told us that I of 0 equals I naught. So let's see what that forces C to be. So we're going to get I naught is equal to S over 1 plus C e to the 0. So I naught is S over 1 plus C. So if we just do a little bit of algebra on that real quick, we get 1 plus C is equal to S over I naught, or C is equal to S over I naught minus 1. And I'm going to get a common denominator for that just because it'll be better for us when we go and try to see what's going on to this thing, with this thing, as we go to infinity. So are we good with C? Any questions on that? All right, so let's put that in for C. So we now have I equals S over 1 plus S minus I naught over I naught e to the minus SRT. I'm going to multiply everything by I naught to get rid of that fraction inside the fraction. So we get I is equal to SI naught over I naught plus S minus I naught e to the minus SRT. So that's what this is going to look like. And what's nice about having this form right here is we can adjust this to whatever, right? You give me a different initial amount of infected people, I put in a different I naught. You tell me a different number of susceptible people, I put that S. We have our transmission rate or whatever we want to call R, I can adjust that, but here is the formula. So now the question is, what happens to that as T goes to infinity?
You're just left with the susceptible population.
Yeah, because this bit, the e to the minus SRT, that's going to go to 0. That's going to drop down to 0. So we're going to get 0 times some stuff, whatever. So we're left with SI naught over I naught, which then the I naughts cancel, and we're left with just S. So the limit is T goes to infinity of I is going to equal SI naught over I naught plus 0, which is S. So over time, we'll get to the point where all of the susceptible folks have gotten it. All right, so does that make sense?
I'm sorry, how did the S minus I naught in the parentheses go away when we had e to the 0?
Sure. So
I'm sorry.
this bit right here, the e to the minus SRT, if we have e to the minus SRT, this is the same as 1 over e to the SRT. And so as t gets large, e to the t gets really large, and 1 divided by a really big number drops to 0. Okay?
Missed it. Thank you.
Yeah, you're welcome. All right, so there's number 29. So let's go look at number 30, because number 30, that's the interesting one. And this is the more realistic one, because now we're going to include something that's fighting the infection. So let's look at that again. Share my screen here. And I like how this starts. They go, ooh, the result of 29 is discouraging, because basically it just says that eventually everybody ends up getting it. And well, I mean, that's reality though, right? Like you think about this COVID that's going on right now. If we don't figure out something that actually fights it, so we don't get some sort of a vaccine or anything else, any other kind of preventative measure, then yeah, eventually everybody's going to come down with it.
Except for a certain level of herd immunity, right? Like, doesn't a certain level of, like, a cluster of people having it protect others from getting it? That would be a whole nother.
Isn't the percentage like 95? It has to be like 95% of individuals have to have, or like have to have some sort of immunity for herd immunity to be a thing.
Yeah, and the whole idea of herd immunity is that Well, let me stop sharing for a second. I'd rather talk to you this way. So the whole idea behind like herd immunity and all that, it's kind of, there's multiple aspects to it, but part of it is you don't have enough hosts to actually keep that virus viable, right? Like let's say 75% of the population now has antibodies such that when the virus comes into their body, it basically just dies off, right? So now random person who has not been exposed to the disease doesn't run into people that have it, because there are all these group of people that can't have it anymore because of immunizations or whatever. And like that's why things like smallpox and measles and these things that we already have immunizations for, that's what keeps it so that it doesn't get going crazy. Now, you have noticed that recently there's been that uptick in things like measles, which corresponds to sort of the anti-vax movement. Now that we've got more people that aren't vaccinating their children, we have more unvaccinated folks, which means there are more bodies that can host like the measles virus, so that then it's just more prevalent and you're more likely to run into it. And so that kind of gets at something else I mentioned with populations of there's that threshold. You have to have a minimum
it's
number.
Almost just like you're hitting a threshold. Doesn't mean it's the entire population. It's just like the amount that is needed to keep the virus going per se. It's like their ability to keep like reproducing within a set amount of people, and then having the availability of having that next victim.
Exactly. It's kind of like we're removing the concentration of susceptible people, right? We're diluting it basically by having herd immunity. It's just that there are so many more that can't be carrying it and that can't pass it on, that it's that much more unlikely.
Yeah.
All right. Well, let's look at what happens now. Like it said in the homework here, when we do throw in some sort of a method of fighting the infection. So if we look at number 30 now, this one, it says, suppose that we're still spreading according to this model, but there's a medication that cures infected population at a rate proportional to the number of infected individuals. And that's what you can see in this formula. You saw the RI to the S, or times S minus I. So that's the spread, just like before. But we're removing infected folks. That's what the minus is. We're losing infected people because they're getting the proper medication or treatment. And they say, again, it's proportional to the number of infected individuals. That's why it's Q times I. And so Q is going to be some sort of a, I don't want to say cure rate, because it's not necessarily we're curing this, but it's healing rate, whatever you want to call it. Okay, but it says Q is a positive constant. We want Q to be positive because otherwise, if Q is negative, we're adding more infected people, which if our medication is doing that, it's not a good medication. Right? All right, so we get a slightly different formula now, and let's see what it's asking us to do. So it says first, choose R and S to be positive, and by plotting direction fields and solutions of this thing on suitable rectangular grids, verify that if I is any solution such that I of 0 is greater than 0, then the limit is going to equal S minus Q over R, if Q is less than RS, and 0 if Q is greater than RS. And then it says in part B, to verify the experimental results of A, use separation of variables to solve it with an initial condition. Well, I say we just solve it. Let's just jump straight to the, let's solve this thing. And then we'll use that to look at what happens as we go to towards infinity. And they do give us a little hint there, right? Where they say there are 3 cases to consider, where Q is either equal to RS or bigger or less than. And we'll see why that has to be when we go and we actually solve it. All right, so I'm going to stop sharing. We'll go back to the whiteboard. So I just know Monty just put in the chat, boo. What was that referring to?
That was back when you were talking about anti-vaxxers.
Oh, okay. When I share the screen, I can't see the chat window, so I'm not really sure what's going on. But yeah,
I wasn't booing you. You're doing great.
No. I didn't think so. I thought you meant something along the lines of we're going to have to solve this or some such thing. But yes, I definitely have opinions about anti-vaxxers that I'll be happy to share with you sometime. I'm sure you know what those opinions are.
Many of us share that opinion.
All right, so this guy, again, let's write this thing up. So we've got r prime equals. We've got the r times I times s minus I like before, but now we've got minus qi. So what we're going to want to do is exactly what we did before, which is separate this thing. Notice that all of this is in terms of I, so we can go ahead and drop that down, and we're going to get di over, and I'm going to go ahead and multiply this out. So we get rsi minus ri squared minus qi, and that's going to equal, I'm going to call it t dt, because we really want to know how this is changing with time. All right, I'm going to do one more thing. I'm going to factor out a minus sign from all of this. So I get a di over, I'll put the minus out front, ri squared plus qi minus rsi. Again, that equals dt. And so what we need to do with this is try to factor and do partial fractions, but I can pull out an I. So I'm going to get minus di over I times ri plus q minus rs. And I'm going to put those in parentheses just because I want to highlight the fact that these things both came from that I term. All right, so any questions on the algebra so far? And that's all we're doing right now. We're just doing algebra because the next step with partial fractions is to split this thing apart and then try to figure out the fractions that add to this. So I'm going to run back to the top, and I apologize. This is going to be kind of this revolving top to bottom of this problem. So if at any point you're not sure about where we are, ask, because it's going to get erased not too long in the future. So now we're going to do that old A over I plus B over Ri plus Q minus Rs. And we need that to equal, I'm just going to make it equal 1. I'll move that minus sign over to the other side because it'll be easier to deal with the minus sign over here. It just becomes a minus t. So then algebraically, we're going to get A times Ri plus Q minus Rs plus B times I. And we need that to equal 1. Because that's the top of what this fraction is. So I'm going to do the trick of plugging in I values. Like if I plug in I equals 0, these things all go away, and I get A times Q minus Rs is equal to 1. So I just did I equals 0. So we get A times Q minus Rs is equal to 1. So A is going to be 1 over Q minus Rs. So that's what's going to go in here for A. And then I need to plug something else in for I. I think I'm going to plug in No, let's just multiply it out. So if we look at the I bits, we have A times R plus B. So here's our ARI, our BI. And I know that this has to end up equaling 0 I, because there are no I's on the other side. So that just means that AR plus B equals 0. So B is going to equal negative RA. And we just found out A. So B is negative R over Q minus RS. Talk about algebra hell. All right, so how are we doing? We okay with the algebra? Did I make any mistakes? Please, heaven, no. All right, so now let's put these A and B in here so we can see what this differential equation looks like now. So I'm going to erase kind of through the middle. So we've got A over I. So that's going to be 1 over Q minus RS times I plus B over all this stuff. So that's going to be a minus R over Q minus RS times RI plus Q minus RS. And this is all DI is equal to negative DT. So I really just changed this fraction we've got near the bottom. I split it apart into these two pieces so that I'm going to be able to actually do the integral a little bit faster. And I'm going to do one more thing before we actually integrate. I'm going to get rid of this Q minus RS. I'm going to multiply both sides by Q minus RS. And so if I do that, then this will look a little bit better. We're going to have 1 over I minus R over RI plus Q minus RS is equal to RS minus Q dt. And I changed the order of these because I had the minus sign. I think it'll just be a little bit easier if we do that. All right, well, I warned you, remember on the homework set, I said number 30 is kind of complicated. I wasn't lying. But now we're ready to integrate. So if we integrate both sides, we're going to get the natural log of I. We're going to get minus the natural log of Ri plus Q minus Rs. This is nice because the derivative is on top. And then on the other side, we're going to get Rs minus Q times T. So now we can combine the logs.
Bruce.
Yeah.
What about plus C?
Fine. Plus C. Now can I combine the logs? Am I allowed to do that now, Thea?
Always.
All right, thank you. All right. So that equals the Rs minus Q times T plus C. Whew. All right. So now let's do the whole E business. So if we convert this to exponential form, I over Ri plus Q minus Rs, that's going to equal C e to the Rs minus Q times T. And I'm just going to leave it like this for right now. We won't bother solving for I just yet. But let's do solve for C, because this was an initial value problem. Let me go back and look at what it said. It said that we've got I of 0 equals I naught, which is positive. So let's put that in. So we know I of 0 equals I naught. So we're going to get I naught over Ri naught plus Q minus Rs is equal to C e to the Rs minus Q times 0. Well, that's e to the 0, which is 1. So we know what our C is. Our C is equal to I naught over Ri naught plus Q minus Rs. So let's put that in. So we now have I over Ri plus Q minus Rs is equal to I naught over Ri naught plus Q minus Rs e to the Rs minus Q T. And isn't that pretty?
Beautiful.
So now you tell me all these different rates. You tell me the susceptible population, the infection rate, the curing rate, how many were initially infected, all that good stuff. I can plug it in, and we got it. So now let's look at what happens as time goes on, right? Because there were if you remember that part of the question, it basically said we want to look at what's happening as t goes to infinity. And they told us to look at the 3 different cases. But now you can probably see where those cases come in. It said we had to look at when Q equals Rs, when Q is bigger than Rs, and when Q is smaller than Rs. And where that's coming in is this exponential piece. It totally depends what Rs minus Q does. Because think about this. As t goes to infinity, this thing is going to grow. It's just going to blow up if the exponent is positive. If that exponent is negative, it's going to drop to 0. So if you look at the conditions on that, when is it positive and when is it negative? Well, if we look at the positive, so here's case number 1. This is going to be when Rs minus Q is greater than 0. Well, that's when Rs is greater than Q, which is one of the 3 conditions that they said we needed to check. But in this case, as t goes to infinity, what we're going to get is I over Ri plus Q minus Rs equals infinity, because we've got a positive exponent. And if this fraction is going to be such that it goes to infinity, that means that I has to go to infinity. So if RS is greater than Q, this is going to grow without bound. So think about what that means in the real world, or what that means in terms of situation. So remember, S was the number of susceptible folks. So R times S, that's, you know, whatever this growth rate is times susceptible folks. But that's basically a measure of how people are getting infected. The Q, that was our healing rate, for example, or if we want to call it that. And so what this is saying, when we have RS is greater than Q, is that people are getting sicker faster than we can heal them. So there's case number one. Case number two. So for case number two, let's go with the other side. Let's go with RS minus Q being less than 0. And now this thing, we're going to have, when we plug in infinity, e to the negative infinity. And that's going to drop to 0. So all of this ends up equaling 0. So if we take this fraction, we've got this fraction equaling 0. Well, that tells us that the top has to be 0. And in this case, we're going to get I goes to 0. So think about what this is saying. Now this is saying that the infected folks, we're getting fewer infected folks than those that we're healing. So if we're able to heal more people than those that get infected, then yeah, eventually our infected number should drop to 0 because we're able to keep up with the disease, right? Anyone who's getting the disease, we can still take care of. So there was case number 2. So then what about the last one? What about case number 3, where this is equal to 0? So now we're in this situation, this real world situation, where we're basically healing people at the same rate at which they're getting infected. They're pretty much linked together. So what should you expect should happen here? What do you think is going to happen?
Does it go to 1?
Okay, so if it goes to 1, the E bit will go to 1, but our infected value should hit some sort of a constant. What that constant is, we don't really know. We'll be able to find it using this formula. But we should expect that it kind of levels out because we're healing people at the same rate that they're getting infected.
Mm-hmm.
So there's that balance. It's just going to kind of level off. So let's see what happens. In this formula, this E bit is now going to be 1 because we've got e to the 0, which is 1. So we've got I over Ri plus Q minus Rs. That equals I naught over Ri naught plus Q minus Rs. But even better, we can go a little bit more with the simplification because the Q minus Rs, I know what that equals. If you come back and you look at the top, we were assuming Rs minus Q is equal to 0. So Q minus Rs is also 0. So this is going to give us I over Ri equals I naught over Ri naught, which all that stuff cancels. And we're left with 1 over r equals 1 over r. And this should make you not very happy, because this doesn't really tell us anything. So here's the problem with this case. I guess this was case 3. With case 3, we actually have to solve it in a different way. I don't know if you remember, but when I first started solving this, if you go back and you look in your notes just a few steps up, when we solved it, I ended up multiplying both sides of the equation by rs minus q to clear some fractions.
Mm-hmm.
And in this case, that means I just multiplied both sides of the equation by 0. And that's like the ultimate no-no, because we could take something that's false and actually make it true. So what we're going to have to do is we're going to have to back up, and we're going to have to look at the differential equation before I multiplied by that q minus rs. So this is where I'm going to ask you for a little help, because I don't want to have to blitz through all the algebra again. When we did the partial fractions, and we ended up with the A and the B stuff that then we put together, help me with this. It was like 1 over
Q minus RSI minus R over Q minus RS in parens. And then next set of parens is RI plus Q minus RS.
But look like that.
Yeah.
And that was equal to dt or minus dt.
Yep.
All right, well, even look at this place. What happens when rs minus q is equal to 0?
No good.
Yeah, it's no good because we're dividing by 0
Yeah.
on both sides. So even at this stage of the game, we can't use this result. So we have to back up even further. So we go, no, that's no good. So let's go back to the original differential equation. I prime equals Ri times S minus I minus Qi. And what I'm going to do is I'm going to distribute through here. So we get RSI minus Ri squared minus Qi. I'm going to lump the bits with I together. So we get I prime equals Rs minus Q times I minus Ri squared. Now we're going to go with the Rs minus Q equals 0. So if this equals 0, that's gone. And we're left with I prime equals minus Ri squared. So this one's kind of brutal because we still have to backtrack all the way to the original differential equation and see that we're going to get a completely different answer. This thing, when we separate it, is going to give us something that doesn't lead to logs whatsoever. So let's see what that actually does. So if I separate, I'm going to get di over I squared is equal to minus r dt. Now when I integrate, I'm going to get negative 1 over I equals negative RT plus C. Oh, that's for theta. So if we solve that for I, we're going to get I is equal to 1 over C plus RT. I know it should be technically a minus C, but since C is arbitrary, I'm just going to leave it like that. So now let's get our initial value. Let's figure out what C is. So I of 0 is equal to I naught. So from this, we're going to get I naught is equal to 1 over C, since T was 0. So C is 1 over I naught. So we get I equals 1 over I naught plus RT. I'm going to multiply by I naught just to get rid of that. So we end up getting I is equal to I naught over 1 plus I naught RT. So that's the solution if Q is actually equal to RS. So now let's look and see what happens as T goes to infinity. But before we do that, any questions on how I got here? Again, a lot of algebra. But this case is completely different. It ended up giving us a completely different kind of solution. All right, so now what happens to this? As T goes to infinity, what happens to I?
It approaches 0.
Yeah, it also goes to 0. So just like that other case, I guess it was what, case 2? This case also goes to 0. So this was one where we're basically curing people at the same rate as they're getting infected. So why does that still drop down to 0? I'm getting a lot of...
The growth of the disease is not... Trying to think of the right way to word it.
Well, let's think about what they were telling us with the formula. I'm going to switch to this image. So think about what they were telling us, that this growth rate, or the change in the infected population, part of it was dependent upon how many people were still left to get infected. There was that S minus I. So realize as people are getting infected, the susceptible numbers are dropping. But all these infected people, they are being removed from the infected as well. So our susceptible group is dropping, which means our infected group is dropping. And this gets at kind of that herd immunity idea. There are fewer and fewer infected people around, which means it's less and less likely that someone can get it, because anyone that ends up getting it, we cure. They can't pass it on anymore. And so eventually it tanks off. So this is where we are right now in our current situation, is frantically trying to get that R, or that Q, and get that Q big enough, right? Because we want that RS minus Q to be negative, or at least 0. And so the whole flattening of the curve, we're just trying to buy some time for that to happen. So that can be from immunizations to antibody tests that let us know better who's got it and who doesn't, so that we can separate them or whatever. But that's kind of where we are. So that's why I gave you guys number 30, is because I wanted you to see how we can actually use differential equations, this class that you just are taking because you have to, and yet it really applies to the real world. And there's not much more real in our world right now than this kind of a problem. So anyway, better for 30. I know, Trey, you asked for this, but I think everybody wanted to see it. Are we feeling pretty good? Better? Yeah, get some thumbs up. All right. Complicated, no doubt.
right? This is the kind of thing, though, that technology would integrate for you pretty easily. But it's really the letters that we have to watch out for. But it really illustrates why we had to worry about those different cases. If we had not thrown in those letters, we wouldn't have necessarily seen why that mattered if we'd just been told a specific, you know, growth rate, healing rate, susceptible population, and so on. All right, so there you go. So I think we just talked about all the questions you guys asked me about. Did I catch them all?
Yeah.
Anything you missed? All right, cool. Well, then I think we're going to go ahead and keep going. We're going to continue with where we were before. If you recall last time, we were looking at equations that, while not separable, turned into separable if they were the right form. And I showed you last time Bernoulli equations. And Bernoulli equations were those that were equal to some multiple of y to the r. So if we've got basically like a linear chunk like we're used to, but then that equaled some sort of y to the r times some function of x. We saw that there was a way of solving them. The Bernoulli was the same as before, where we throw in an integrating factor, u, just the u comes about in a different way. So the next one I want to show you are another group that are called homogeneous nonlinear systems. And you might have had your ears just perk up there and go, well, wait a minute, we've already talked about homogeneous. What does homogeneous mean in terms of what we were doing before when we were solving linear equations?
Where your g of x is equal to 0.
Yeah, where it equals 0. So we just got a bunch of people throwing that out in the chat. So that's where it equals 0. Well, when it comes to nonlinear, homogeneous can actually mean two different things. And I'm going to apologize on behalf of mathematicians for doing this to you. Again, don't blame me. I didn't come up with this. But we use homogeneous to mean two different things in differential equations. One is it equals 0. Okay, so great. But there's another way that we define homogeneous that pretty much the context for this class is going to be when we're talking about nonlinears. And it goes something like this. Let me switch to the board. So if we've got a nonlinear that we call homogeneous, actually, let me do this. Let me give you an example of one. Because I think if I give it to you, then it'll be a little bit easier for me to talk about why this is homogeneous. But this is an example of a homogeneous nonlinear. And I'm going to put this with nonlinear because with linear, it specifically means equal 0. So here's an example of one. It'd be y prime equals x plus 3y over x minus y. So first things first, you should totally see the nonlinear. Right? This is nonlinear. But the reason that this is called homogeneous, and what it means in this context, is that you can write, if we have y prime equals f of x, y, we can actually instead write this as a function of one thing, which is a function of y over x. So basically, we can create a new variable, say, call it u, where u is equal to y over x, so that this thing is in terms of only that one variable. So that's what it's going to mean for this to be homogeneous when we're talking about nonlinear, is that by doing this transformation, this substitution, we can turn this thing y prime into just a function of this new variable, which I'm calling u. So here's why we like doing this, by the way. If I rewrite this as y equals u times x, then y prime
is going to equal u prime times x plus u. X is just x. You don't have to worry about that being a function, but we do have to do the chain rule, and that's what this is, which means our differential equation then is y prime equals, or sorry, not y prime anymore, u prime times x plus u equals g of u, and this thing is separable because we've got u prime times x equals g of u minus u, and now we can separate it. And that's kind of the whole point here, is trying to show you examples of things that aren't separable at the start that can be turned into separable with this change. So again, I apologize for the fact that we're using the same term for something different, same word for something different. But for these homogeneous nonlinear, basically what you want to look for is there a way that we can turn this into a function of y over x's? Because if so, then we can separate. So let me show you why this one up here, this one I first showed you, is actually homogeneous. What I want is y over x's. So what I'm going to do is I'm going to multiply top and bottom of this by 1 over x. And so if I do that, then notice how the y over x's, if I change those into u's, this y prime is only in terms of the y over x. So this is going to be the goal with these, is try to make it as things of y over x so that we can then do this separation. So let's finish this one out. Now that we're already almost there, let's change it into these u's and see what the solution is going to be. So for the y prime, you're always going to put u prime x plus u. And then that's going to equal, in this case, 1 plus 3u over 1 minus u. So let's do a little bit of algebra. Let's get this thing so we get the u prime all by itself and then separate it. So we're going to get u prime x is equal to 1 plus 3u over 1 minus u minus u. And if I get a common denominator, this is going to be the same as 1 plus 2u plus u squared over 1 minus u. So the u squared, that came from the minus u down here times the minus u. And then the 2u, we've got a minus 1u plus 3u. So now if I separate, I basically have to bring the 1 minus u over and also the 1 plus 2u squared plus, or 2u plus u squared. So I'm going to flip that over. I'm going to get 1 minus u over 1 plus 2u plus u squared du is equal to dx over x, because I have to divide by x to move that over. So by the magic of that substitution, we now have a separable differential equation. But you can see that this isn't going to always be the case. It really is going to depend upon what the original differential equation is. But this is an example of one where we can do this. Well, I don't want to leave it here. Let's go ahead and solve this thing. So if we wanted to integrate this, we'd have to do partial fractions. This is one where if you factor, you get u plus 1 times u plus 1. And just to remind you, again, I imagine you probably just jump to some technology to integrate it, and that's fine. But for this guy, we would have to do the a over u plus 1 plus b over u plus 1 squared when you have a repeated factor. And I can see JP just kind of chuckled because I think he remembered having to do these horrible things. But when they repeat, we have to do something like that. But it's the same idea. You get your common denominator, build your system, you can break it apart, whatever. But I just want to jump to what we get when we integrate this. Obviously, the right-hand side is nice and easy. That's just natural log of x. On the left-hand side, we get the minus natural log of u plus 1, then minus 2 over u plus 1. You can see where these are going to come from, right? The part with the u plus 1 on the bottom gives us the natural log. The one with the u plus 1 squared is going to give us a u plus 1 on the bottom. The specific numbers are going to come from whatever a and b we needed to split this apart. Okay. But anyway, that's the integral on that side. On the other side, we just get natural log of x plus c. But we're still not done because this is now in terms of u, but we want to go back to what we were originally doing. And we had that u was equal to y over x. So if we put that in, we get minus natural log of y over x plus 1 minus 2 over y over x plus 1 equals the natural log of x plus c. And if you're so inclined, go ahead and find an implicit or an explicit form for this. I'm going to leave it in implicit form, especially since I don't have any kind of an initial condition. All right, so here's an example of one of these homogeneous nonlinear. But let's do another one because I want you just to sort of see the process. But it's always get it in terms of y over x. Because if you can get it into y over x, then you're good. All right, so here's another example. So this one we're going to have y prime is equal to x squared plus 3y squared over 2xy. And the fact that this one's also a fraction, that's purely coincidence. It's just what I wanted to use. You can get plenty of these that are not fractions themselves. But let's see if we can solve this guy. So first things first, let's see if we can write it so that we're in terms of y over x's. So does anybody see the algebra step we're going to have to do here?
Conjugates?
Nope, no conjugates.
No. Fuck.
What did we do last time?
Multiply by 1 over y squared.
Okay, so last time we multiplied by 1 over x. And so, Mikey, you're almost right. Instead of 1 over y squared, we want to multiply by 1 over x squared.
Oh, yeah, right.
And what's going to tell you that is look for the highest power of y. Because if we want to get y over x, we need to have an x for every one of the y's. So in this case, we're going to multiply by 1 over x squared on top and bottom. And what that's going to do here is give us a 1 plus 3 y squared over x squared divided by 2y over x. And now you can see how this is going to work when we do our substitution. So if we let u equal y over x, this is going to give us u prime x plus u is equal to 1 plus 3u squared over 2u. So when you have a fraction, in one of these situations where you've got a fraction with x's and y's, just look for the highest power of y, divide by that highest power of x. Because if it's homogeneous, if this is going to work, that's what you're going to have to divide by. So you can try it. If it fails, okay, it fails. But if not, then we're good to go. So just like before, we'll move that u over. So we get u prime x is equal to 1 plus u squared over 2u minus u. If I get a common denominator again, this is going to give me 1 plus u squared over 2u. So then the separation, once I move things around, I'm going to get 2u over 1 plus u squared du is equal to dx over x. So here's something else I want to point out. If you have one of these things that is homogeneous, the bit with the x is always going to be dx over x. Always. Because the whole point is that whatever this other function is, it's all in terms of u. So you're not going to get any other x's. And so the only x shows up from the product rule with our initial substitution. All right, well, now we're ready to integrate. The left-hand side is beauty. It's just the inverse tangent of u. Oh, I lied. This is not the inverse tangent. That's a natural log. Natural log of 1 plus u squared. And then on the other side, we get the natural log of x plus c. So we can go ahead and do our e trick. So we get 1 plus u squared is equal to e to the natural log of x plus c. So we've got 1 plus u squared is equal to c times x. So the plus c, that's the same as multiplying by e to the c, which becomes a new c. And then the e to the natural log of x is there. So now let's substitute. So we put in our y over x. And this one we can actually get all the way to an implicit form. Pretty easy, or explicit form, I should say. So let's do that. So y squared over x squared, if I move the 1 over, is equal to cx minus 1. Multiplying by x squared. We're here. So then depending upon our initial condition, we're going to get plus or minus the square root of cx cubed minus x squared. And again, which one of these we use will totally be determined by what our initial condition was. If we end up with a positive y, when we plug in our x, we use the positive square root. If we get a negative y, we put that in as well. All right, well, there you go. So this is just another form that even though it starts as non-separable, ends up becoming separable if you just do this substitution. But the other thing I want you to notice, like when we wrote that out, it was u equals y over x. Look at it as the y equals bit. I just want you to look at this for a second. And notice we're doing the same thing that we've done for all of these, which was we multiply by some unknown u. So that trick of multiplying by an integrating factor, I think this is now the 4th time we've seen it. We're only 2 weeks in, and we've already seen it 4 different times. You're going to continue to see it as we move through because it's a really, really common technique. And it's something that's pretty easy to do where you just go, all right, I don't know what the function looks like. So how about I just multiply it to something I do know and see what that forces. All right, so how are we feeling about these homogeneous, even though they're not really homogeneous like you think of as homogeneous? You gave me a thumbs up. I'm getting a couple of head bobs. We're feeling all right. All right. Okay, so we're kind of at the end of a section, and like last time, I don't really feel like diving in to the next one just yet because we're doing just fine in terms of time. So I think we're going to pause here, call it a day. So let me go ahead and stop recording here, and then we'll chat.